Hi there. Welcome back to my training series entitled Understanding EMV. Okay, we are currently in the EMV acquiring section. This is video 23, and in today's video, we are going to be covering the EMV transaction, step 11. Okay, so let's get straight into it. Excuse me. Okay, so let's do a quick recap. Okay, so we know Bob is waiting in the store to complete the payment, for the purchase of a pair of socks. And the first thing we did in the transaction was to establish which technology we will be using. And obviously, in this case, we opted for an EMV transaction. Uh, Once we chose the technology, we then identified which virtual cards were available to process this transaction, on Bob's card, and we chose, in our instance, the primary virtual card or primary application on the card, which was a credit card. Okay. Once the application was selected, the terminal and the virtual card or the application then had a bit of a conversation where they exchanged important information with each other, which took us to step 4, where the terminal kicked off a process called offline data authentication or card authentication methodology. And in this process, the terminal tried to establish that the card being used is a genuine card issued, by the relevant issuer, that is not a counterfeit or a clone card. Step 5 was the phase of the transaction where we validated that the transaction itself was valid. There were several things in terms of area of usage and the type of transaction, etc. After assessing that, we went into step 6, where we assessed, that is Bob the authorized card holder? Is he the person authorized to use this card? So we verified the card holder, which took us into step 7, where the terminal did some risk management, based on the preceding steps, just to understand the inherent risk within the transaction. Uh, as a result of that, it formulated a decision that that the terminal thought that um, how should this transaction proceed, and it sent this decision in the form of a request or suggestion to the card, right? So on the terminal, I'm saying, okay, card, I think this transaction should go online, or I think this transaction should decline, etc. Okay, just remember the card makes a final decision, so this is in the form of a request, which takes us through to step 9, where the card does its own risk management. It undergoes a phase called card action analysis, and part of this obviously does take the terminal's request into consideration, but it performs additional checks on its own, independent of what the terminal had done. This then brought us into step 10 of the EMV transaction, which is the first gen AC phase of the transaction. Now, three things could have happened at this phase, right? So the card could have decided to approve the transaction, decline the transaction, or send the transaction online to the issuer host for additional input. Now, had the card decided to approve or decline the transaction offline, this would have been the end of the transaction, and the whole transaction would have completed. But for the purposes of this training, let's assume that the card did actually generate an ARQC, authorization request cryptogram. So it was basically a decision to send the transaction online for additional input from the issuer host system. And so what had happened at the end of this would have been that the terminal would have generated an ISO 8583 message. It would have attached all the relevant transactional data, including chip data. And it would have sent this upstream to the acquirer switching system, which in turn would have passed it out to the issuing bank's switching system, assuming that the issuing and acquiring banks are different here. And the issuing switching system would have then passed this transaction to the issuer host system. Okay? Which brings us into today's video, which is just understanding how the issuer host system makes a decision now. Okay. So we, we said that the ARQC is sent upstream to the issuer in the auth request message along with some other data elements. The issuer receives the authorization request, and at this point it does a few checks, right? So the first thing it'll do is uh, account level checking. It'll do some risk checking, PIN verification if necessary, and obviously at the end EMV checking, right? So of particular interest in this video is online mutual authentication, OMA, leg 1, okay, which is also referred to as ARQC validation. Okay, let's talk a little bit more detail around each of these checks. So account level checking. The issuer system will check the PAN, it will map it to the associated account linked to this card, and it will determine are there sufficient funds in this account to successfully complete the transaction. So, do the funds in the account, um, does it equal or exceed the value of the transaction amount uh, that's come through on the request? Right? Is there sufficient money available um, to allow Bob to make this purchase? Okay. Next is risk checking. So the issuer system checks if there are any fraud statuses on the relevant account or if there's an unusual spending pattern. So typical things are, has this card been reported lost or stolen recently? Is the account in default? It's a credit card, and the if you have a credit card, you're obligated to make a minimum payment, every month. And if the card holder has missed this, the bank actually could take action, freeze the account, and start declining transactions. Is the card being used in a different country or city than the details available in the system? Let's assume that if the card is issued in South Africa, and the transaction all of a sudden pops up with the location of the transaction being in Texas in the USA, uh, you know, uh, would the issuer system deem this to be suspicious, right? So, did the cardholder notify the bank that he would be traveling to the States, he would be in Texas over this period of time, or is this a transaction that has arrived completely out of the blue? Okay. And some banks even take this one step further where they can identify patterns. So if they've got customers over a period of time, as an example that we've used, Jim, let's say that we've got Bob who's never been to a casino before. He's had the account for 15 years with the bank. And he's never ever used the card in a casino. And all of a sudden, a transaction comes through to the host system from a casino. Now, that could be deemed to be suspicious, based on the pattern that we've identified in terms of of how the customer spends, and so there's an opportunity for the bank to actually, you know, make a phone call the cardholder, and just confirm that it is actually the cardholder at the casino because his normal spend pattern has been broken. Now, not all issuers do this, some do, and it's actually a very good way to combat card fraud. PIN verification. So during the transaction, if when we do the card holder verification step, if the selected CVM was online PIN, 4203, what would have happened is the terminal would have included an encrypted PIN block into the ISO 8583 message, and this would have been sent upstream. The PIN block would have been in field 52 of the ISO 8583 message, and obviously the host system would need to now verify this PIN to actually complete the CVM step of the transaction. And what basically happens is this: so the terminal, uh, you know, appends the PIN block in field 52, and let's assume that the PIN block. This is an actual example from a test system somewhere. So this is what a PIN block looks like. Nothing like a 4 or 5 digit PIN, that we expect to see. Uh, so the issuer host will receive this value in field 52 of the auth request message. Okay. Uh, it then takes the PIN block. Okay. It then takes the PAN and PAN sequence number, applies it against the master key set, which then produces the derived encryption key, and then it uses the derived encryption key to decrypt the PIN block, which will result in a PIN. I've just got 1, 2, 3, 4 as an example. The host system will now generate the PIN value, right? Or in instances where the issuer stores the PIN, it would retrieve that. But generally speaking, we don't do that. We don't store the PIN. We always generate it, on the fly when required. So it could generate the PIN for the card. If there were any offset, it would apply that, and then it would compare the PIN that it decrypted from the PIN block against the PIN that it generated. And if the two match, then we've successfully validated the PIN, which means we've successfully validated that the card holder was genuine. Okay. Next is EMV checking. So the issuer host system should have validations in place to assess EMV data received in online transactions, and to factor this into decisions to approve, decline, or request additional customer verification, where you make a phone call and you basically verify the customer. So the following 2 slides will provide examples of some of the EMV checking that could be done. Just note, these are just 2. There are many dozens that you could actually implement in your environment to make your card program more secure. So example 1, let's talk about application transaction counter. We know this is quite important. So the host system should validate the ATC to prevent replay of messages. Okay. Remember, we spoke of ATC in previous videos. This is a sort of running total of every single transaction the card has performed. It always increments, and this counter is never ever reset, right? So the ATC value for every online transaction must be stored by host and then compared against the next online transaction. Now, the important thing here is the word online, right? So remember, the card is capable of offline transactions, and it will keep a running total of every single transaction. But obviously, the issuer host can only have a view of the online transactions. Okay, so it must take a record every time that this card comes online. So let's do a simple example here, right? So we've got a card that was issued, and let's just say it's got an ATC variance window of 5. So what we're saying is the card is allowed in a maximum of 5 offline, 5 consecutive offline transactions, right? So brand new card, transaction 1. Let's assume, so F stands for offline, N stands for online. Excuse me. So let's assume that transaction 1, the very first transaction ever performed by the card, was an offline transaction. So at the end of this transaction, the card ATC will increment from a 0 to a 1. Okay, but because it's offline, the issuer host doesn't have a view of this, right? So it will keep the host, it will keep its own record of the ATC for this card at 0. So at the end of this offline transaction, because it didn't come online, the host is not aware of it. At the end of the transaction, the host will still have an ATC value of 0. Transaction 2, let's assume it goes online. So we know that the card will now increment it from 1 to 2. At the time it reaches the host's ATC value for this particular card is 0. So in this instance, 2 is greater than 0, right? It's greater than. Okay, so which is good news. And then what will happen is the issuer host will take this value that it received and it will now write it to its own database. Transaction 3, assume that it's offline. We know the card will increment it from 2 to 3. However, the host, the value remains unchanged because it's an offline transaction. It's not aware that an offline transaction was performed at this point in time, so this will remain on 2, right? Transaction 4 is an online transaction, so we know at this point, on the online message, the transaction ATC, the card ATC on the transaction will be a value of 4, right? But the last time that the host took a record was on the second online transaction that came up. So it will compare 4 against 2 and says, okay, look, 4 is greater than 2, which is good news, and then it'll write the 4 to its database so that the issuer host now has an updated value of 4 for the HCC. So I mean, so far so good. Everything seems to be going, the way we would expect a a typical card environment to operate. Right. So let's throw some funnies in there now. Now the host gets a transaction coming in. I'm just calling it transaction 5. It's an online transaction, and on the transaction it receives a value saying that the card's HCC was 10. Now, is 10 greater than 4? Yes, it is, which is good news. However, the problem is that we said the variance is 5, but 10 minus 4 is 6, right? So it's greater than the acceptable variance of 5. So this is suspicious because we know the card is not capable of conducting five complete or more than 5 complete transactions offline. So in this case, we're saying that there was 6. So what should happen is the host should decline the transaction, say, no, look, this looks suspicious, and what it will do is it will not update its record of the HCC. It will maintain the previous one because it deems this to be suspicious. Okay. Let's look at transaction 6, which is also an online transaction, and the card HCC comes up now with a value of 3. And the host says, I've historically got a value of 4 stored. If I compare 3 to 4, okay, there's a problem here because 3 is actually less than 4. Okay, and that's not acceptable. Okay, so that's suspicious and it should decline the transaction, right? Or it should request for a decline to occur. And once again, because the circumstances were suspicious, it will not update this value with the new value. It will maintain the original value, right? Transaction 7 comes online. The card HCC is 4. The host compares the new card HCC with the existing database record and says, it's equal to, this is a problem, right? Because for every transaction, the HCC has to increment. The new card HCC always has to be greater than the existing one, right? So in this case, it's equal to, once again, suspicious condition that the issuer should actually, regard this as suspicious and actually respond with a request for decline on the transaction. Right. Transaction 8, just to establish some normalcy, it's an online transaction. It comes in with an HCC value of 6. The issuer host says, let's compare 6 against 4. Yes, 6 is greater than 4, and the difference is 2, and which 2 is within the variance of 5, so therefore it looks good. Don't see a problem with it, and what I will do is I will update my record on my database to match the last known valid value that I received. Okay, I hope that makes sense. Let's move on to our second example, where we compare EMV tags on a transaction message. So, typical example, fraudsters could execute something called a wedge attack to change data as it moves between the card and terminal to show that CVM was successfully performed at a terminal. It's not a very common thing. It requires quite sophisticated hardware, and it's not overly practical, but it is something that we do need to cater for, right? So the host system should check TVR. Remember, TVR is the view of the transaction from the terminal's perspective, right? And only the terminal's perspective. So let's say that the fraudster changed byte 3, bit 8 of TVR, okay, to indicate that cardholder verification was successful. So actually, it was unsuccessful, but somehow they managed to attack the data and change it. They changed the TVR to say, look, it actually was successful, right? What the host system should do is not take it at face value. It should actually now check CVR. Now remember, CVR is a record of what has happened in a transaction from the card's perspective. So if it looks at byte 4, bit 5 of CVR, and in this example, I'm using the MasterCard MChip Advanced format, byte 4, bit 5 will show that the offline PIN verification has failed. Right? So initially, TVR and CVR both said, offline PIN verification failed. The fraudster changed the TVR to say it's successful, but what the issuer host now sees is a discrepancy. It sees one the one participating entity saying CVM was successful, and it's saying another one, the card, saying it wasn't successful. It wasn't successful. So because of discrepancy, this is suspicious, and it should be actually a reason for the issuer host to request a decline for the transaction. Right. The same principle would apply to various other tags, right? So it's not just comparing TVR against CVR. Yet there are lots of tags and fields on the ISO 8583 message that can be compared against one another, just to ensure that there's consistency. And the minute you find any conflicts or inconsistencies, this should be regarded as suspicious. Right, let's talk a bit about online mutual authentication now. OMA, leg one. OMA stands for Online Mutual Authentication and refers to the process of card and issue authentication that occurs during online chip transactions, right? So it's mutual. So it's there's two parts to it, right? There's card authentication and there's issue authentication, right? So there's two distinct legs. Leg one, which is what we're interested in this particular video, is where we say that the host system authenticates that the card being used in the transaction is genuine. Right? It's also called ARQC validation. Leg two is where the card authenticates that the response it received actually did arise or emanate from an authorized issuer host system. So in other words, the message it received is genuine. Right, and this is leg two, and this is also referred to as ARPC validation. So we'll focus on leg one for the section. Okay, it is done by the issuer host system, and it verifies the ARQC that is sent up in the online transaction. So how does it do that? Excuse me. So the host system will receive an ARQC in the online auth request message, and the ARQC will look something like this, right? The host system then, so it receives this and it stores it temporarily. Okay, it then generates its own ARQC by following the following steps. Okay, it will retrieve the DKI from the auth message. Okay, so basically the right key index, so understand which keys we used for this transaction. Okay, so once it has a DKI, it can identify the master key set, and once it's got the master key set, it can generate the unique DK auth key, okay, by applying the pen sequence number against the master key set. It then looks at the relevant piece of data in the transaction that we used to create the original ARQC cryptogram. Okay, so these fields are available on the auth request message. Okay, so it takes the values and it creates a string from there, right, which looks something like this, right, a string of data. It then encrypts the string using this derived key, and it produces a calculated ARQC. Now at this point we've got two ARQCs, right? We've got the one that the issuer host has calculated, and we've got the one that it received on the online message, and it's stored temporarily. So all the issuer host system now needs to do is compare the two. And if the two match, then we've successfully validated that the card being used in this transaction is a genuine card that was issued by this issuer host system. Okay. So based on all of the checks we've just spoken about, right, the host system will make a decision with regards to how it wants the transaction to complete. Will it ask for a decline or an approval, or will it ask, let's call the customer, let's get more information before we can approve it, right? So this is called an authorization response code. This decision by the issuer host system, an ARC, okay, and it's typically passed back in the auth response message back to the terminal. And you can see it in field 39 of the ISO 8583 response message. So typical examples of these ARCs or authorization response codes will be, obviously a 00, which is what we want to see. It's an approved transaction, O1, refer to card issuer. O4, there's a problem here. It's an instruction to actually take the card away from the card holder. O5, do not order. 51, the very first check, there are insufficient funds, which means that the issuer host can't approve the transaction. And you get a whole host for other ones. So like 91 is one of them. It's generated systematically where there's been a timeout somewhere during the transmission of the message. You get others, 96s, etc., etc. Right. So in addition to supplying that ARC, that 00 approval back in field 39 of the ISO 8583 response message, what the issuer host will also do is create something called an ARPC. Right? So remember, it received an ARQC that the card generated. It will now build something called an ARPC and it will send it down to the card. Okay. ARPC will be used to complete leg 2 of OMA, okay, which we will discuss in the next section. Okay. So in order to create the ARPC, right, the issuer host combines the ARQC and the ARC. It encrypts it with the DK auth that it had generated, and it then sends this ARPC back downstream. It attaches it to the ISO 8583 message so that it returns back to the card. Okay, so in a nutshell, here's the ARQC that we had received. The issuer host has decided that there's no reason to not approve the transaction. So what it'll do is it'll add the ARQC to the ARC, encrypt it under the DK auth, and this then generates an ARPC that looks something like this. Right, so once the host has completed all the checks, it will respond to the auth request message. Okay, and the issuer host, basically its interaction in the transaction is now over. But it won't get involved in this transaction any further. Right. So please remember that it will include the following data back on the authorization response message back to the terminal. Okay, so we spoke about it. We said there's an authorization response code, an ARC, present in field 39. It'll send back some EMV data in field 55 that will contain the ARPC. Right, remember we said ARQC plus ARC encrypted under the DK auth key gives you the ARPC, so it will send it back. And in addition, the issuer host could also send back EMV issuer scripts, which we will also discuss later on, right? And there's any other discretionary data that may form part of the transaction loop, as per, there may be local regulatory requirements or certain issue or acquirer or scheme requirements. Then this discretionary data will also be sent back on the authorization response message. Once the terminal receives the authorization response message back from the issuer host, okay, it is ready to go into the second gen AC phase. Okay, which is now step 12 of the EMV transaction. Okay, and we will discuss step 12 in the next video. Right, so in this video we've just completed the processing around the issuer decision, and we are ready to discuss step 12, which is the second gen AC phase. Remember, step 10 was first gen AC. Step 12 is now the second gen AC, and second gen AC is only ever present on transactions that go online, right? You won't see a second gen AC on a transaction that completes it offline. So yeah, in the next video, we're gonna cover second gen AC. So thank you for spending the time with me on this video, and I look forward to catching you guys in the next one. Cheers everyone, and bye bye.